Hello, relativity friends. This is part two of me trying to understand the fundamental theorem of Riemannian geometry, which states that for any Riemannian manifold, there exists a unique affine connection that satisfied two conditions. And the last time we did the metric compatibility, which says the covariant derivative of the metric tensor is zero in all directions, means the metric tensor's components maintain their values under parallel transport. And we went through examples like this, and we showed this unique affine connection is the Levi-Civita connection. And we did, there we go. The covariant derivative of the metric tensor is equal to zero. Then we did a specific example with polar the coordinates, which was wicked fun. Okay, now here is part two. This special affine connection, the Levi-Civita connection, is torsion-free. Now, this torsion-free thing opens up a rabbit hole, which you can fall down if you wish. It's pretty deep. For me, it simply means the Christoffel, the symbols, are symmetric in their lower indices. So let's look at that. We know the definition of the Christoffel, the symbols. It's the derivative of a basis vector with respect to a coordinate, which is itself a vector, which we can express as a linear combination of its components and basis the vectors, okay? But what is a basis vector? Well, a basis vector is defined as the derivative of a position vector with respect to a coordinate. So if we put this right back in there, we get the second derivative of that position vector with respect to I first and then j is equal to this. But we can swap those because we know that the order of differentiation is not important. We can differentiate first with I and then j, or then j and then I. If we swap these two, it swaps these. So if this is equal to that, then this must be equal to this, which means that these are interchangeable. So it is symmetric about its lower indices. Which one do you say? I guess I say indices. Okay. Then I ran into this. What is the torsion tensor? Oh my. All right. I looked it up, read some about it. It's interesting. So, building on the work of Riemann and Christoffel, Ricci Carbastro, this is his last name, Levi-Civita, that's also his last name. They published their work on tensor calculus around 1900. They assumed an affine connection that is both metric compatible and torsion free. This later was called Riemannian geometry because it had those two conditions were met. Okay. Apparently, Riemann didn't call it Riemannian geometry. It come many, many years after his unfortunate young death. Then, in around 1922, Elie Cartan introduced the idea of a torsion tensor. So this is way after these guys. Cartan showed around this date that the torsion tensor is intrinsically related to the translation group. I'm not comfortable enough with what that means to explain it. I welcome you to look it up, but it is a rabbit hole, I'm warning you. Okay, the torsion tensor is defined as this. It has two distinct parts. So the torsion of, and these, they should be vector fields. So that would be vector field A, vector field B, is the covariant derivative of B with respect to A minus the covariant derivative of A with respect to B minus this thing in brackets, A comma B, which is a commutator, and it's given the name the Lie bracket, Lie bracket. Okay, so what I did was made this very, very simple for me to understand by just doing it with basis vectors and polar the coordinates. Okay, so we're going to let our A, B's be ER and E theta. Now let's do this guy first, the Lie bracket. All right. Now, we also know we can write these derivatives as differential operators the way they do in differential geometry, the partial with respect to r, partial with respect to theta, right? So we do this. We follow the rules of a commutator, which is this acting on that minus this acting on that. We get this expression, okay? We plug in what we need, right? So the partial with respect to theta is z theta. We take the derivative of that with respect to r, and we get this. Then we do the opposite. So this is the partial with respect to theta of ER, that's ER, and we get this. Now, if we put them in a commutator, we get this. So it's this minus that. A negative times negative is positive, and you can see they add to 0. All right? That's a real easy way for me to understand this. Now we're left with this piece. So the Lie bracket was 0, so we're just left with this. So now we have to do the covariant derivatives. All right? So we know how to do that by now. The first thing you do is you write down the partial derivative of this with respect to that. And since we're taking the covariant derivative of a covariant vector, we have a negative sign. Then we have our Christoffel, the symbol, and its basis, the vector. Minus, we do the exact same thing, but opposite, right? So the partial derivatives are with respect to the theta. And here I got a negative times a negative is a positive. We get this Christoffel, the symbol, k r theta, and ek. Now, we just did this above. This is what we just did. That's what that is. So this minus that is 0. We know that. So that just leaves this. So let's rearrange and factor out an ek, and we get this. So if the Christoffel symbols are symmetric about their lower indices, r theta and theta r in our case, then torsion is equal to 0. Now, in the relativity books I have, including the tome of the gravitation book, it says that there has been no experimental evidence that torsion exists in a gravitational field, so it is always 0. So having to understand Élie Cartan's definition of torsion and learning how to use this is not important to me. So I'm not going to do anything about it. You're welcome to. And that's all I got for today. I'll see you later. Thanks for watching.